Hi, welcome back to another day of Math 112, elementary functions, or sometimes we call this course trigonometry because we spend a lot of time talking about our friends, the trigonometric functions. And today we are going to focus on sinusoidal graphs. Now I want to be careful here. Sinusoidal does not mean just sine. So we've talked about a bunch of different trigonometric functions. We've talked about sine and cosine and tangent and secant and cosecant. And we haven't really done much more than define those. What we're going to do today is we're actually going to start talking about what those functions mean as we sort of move away from limiting ourselves to the unit circle. So sinusoidal just means things that are of the same shape as the shape that the sine function will make. And we'll take a look at that, at what we mean by that. So one of the easiest, we're going to develop this in relation to a circle. And so let's think about a giant Ferris wheel, specifically the London Eye. This thing has got a diameter of 135 meters. And I would convert that to feet, but I don't remember what it is. 400 and some odd feet, I think. And it takes 30 minutes to go all the way around. So if you get on here, it takes 30 minutes to go all the way back around. Now, let's talk about the height of a chair on this thing. And what happens as it goes, so just the height, not the x dimension, just the vertical. So it goes up, yeah, reaches the top, and comes back down. And does it again. It goes up, reaches the top, and comes back down. So for each revolution, a chair rises, falls, and then on the next revolution, it repeats it. If we want to graph the height of a chair over time, what we're going to see is that the maximum and the minimum height don't ever change, and that the slope of the curve from maximum to minimum doesn't change. In other words, everything is pretty repetitious and periodic. Sorry, there we go. So now let's remember what we said about the coordinates of a point on a circle and the relationship between sine and cosine. So let's think about this thing being placed on the, on a coordinate plane and centered at the origin. Okay? What's this going to look like? Let's see if my Desmos graph is going to work today. But remember that if we center this thing on the origin, so this circle represents the London Eye, okay? The coordinates of this green point right here, let me put this in projector mode, blow it up a little so we can see better. So let me move my point around a little. So let's see, let's ignore the blue for a minute. So ignore that, and that, and that, and that, and this. This green point right here, its coordinates are given by r, the radius of the circle, times the cosine of the line I'm going to put on right now. Maybe I'm going to put that on. No, I'm not. Okay, if we imagine a line that goes from the origin of this graph to the point in question here, we can think about the angle that is formed between the x-axis and that line. The cosine and sine of that angle are related to the coordinates of this point. Remember that the x-coordinate is equal to the radius times the cosine of the angle, and the y-coordinate is equal to the radius of the sine times the angle. So now I've got a circle of radius 1 here, but the same thing is going to hold for a big circle like the unit, or like the London Eye. If I move my point around the circle, let me put it back down here at 0. And I'm going to take a look at a graph of the height of that point above the x-axis over time. And we can talk about time as time, or we can talk about time as the angle that the radius makes. So the angle between the radius and the point. And so what do we see here? Well, we see that we've got a periodic function. We can see that there's a predictable amount of space between the peaks. So between peak and peak. We can see that the maximum and minimum are related to the height of the circle. And later we'll see that the spacing of the peaks kind of depends on the speed at which the point goes around the circle. This blue line here, remember, was related to the height of the point, which means it was related to the y-coordinate as we went around the circle. The y-coordinate is described by the sine function. This blue line represents the graph of the sine of an angle. So if I were to put on here the function y equals sine A, nah, sounds funky. I'm not sure what's going on. Okay. We're not going to worry about that. But this represents the sine of an angle, and it is developed based on the height of the moving circle, of the point. So we can go back to our London Eye and talk about the height of the chair can be found from r sine theta. And the sine theta, the theta, if we think about a horizontal radius, the theta is the angle formed by the spoke connecting this chair and a horizontal spoke. There's an angle there. The horizontal distance is cosine theta. It turns out that sine and cosine are pretty closely related, and we will look at that. So this is y sine theta. The sine curve, the sine function, y equals sine theta. Domain is negative infinity to infinity. Range is negative 1 to 1, meaning that it oscillates between 1 and negative 1. The period is 2 pi. Now the period, let's go back out here to Desmos. So the period of a sinusoidal function is the distance from peak to peak. And it might be kind of hard to see here. Let me see if I can change that. That's better. So if we look at our sine function, some things to keep in mind. First of all, the sine function it goes to the point 0, 0, and it would continue on in the opposite direction. So the sine function is symmetrical about the origin, meaning that it's an odd function, which means that if we want to look at the sine of, say, negative 2 pi, and we know that the sine of Earth is negative pi over 2. So we know from this graph, and also from our knowledge of the unit circle, that the sine of pi over 2 is 1. Now, think back to the knowledge of the unit circle, and we know that negative pi over 2 is going to be down here, right? At 0, 1. The sine of negative pi over 2 is negative 1. And sure enough, if we were to graph out the sine function, we will get down here to negative pi over 2 and 1 on the sine curve. The period is the distance from one peak to the next peak. And we can see here we've got a maximum at pi over 2 and another maximum at 5 pi over 2. So if we look at the x-coordinates, 5 pi over 2 minus pi over 2 is 4 pi over 2, or 2 pi. So the sine function has a period of 2 pi. What that means is the values repeat every 2 pi. So 0 to 2 pi are both 0. This 0.739, 0.674 will occur again. 2 pi later, we get that same value back. That's because this is all based on rotation around a circle. And we go around the circle every 2 pi radians. Yeah? All right. Let's see what else do we need to know about our sine function. That's about it. So cosine is very similar to sine. Very similar, except that cosine starts at 0, 1. So because the cosine is related to the y-coordinate, it starts at the top here. Now cosine is related to the x-coordinate, my bad. Cosine starts at 0, 1, because if we start down here at x, let's take a look at this. So remember that the cosine is related to the x-coordinate. So when we start down here with my point at 0 on x, and then we go forward, well, we're going backward. But other than the fact that it is shifted, it looks significantly similar to sine. So let's take a look at that. Let me open up a graph. No. Wait, okay. I want a blank graph. Okay, so we just looked at sine. So let's look at y equals sine x. And now let's look at y equals cosine x. And I'm going to change the units on my x-axis so that we've got our usual radian units. Okay, what do we see? Now remember, the red one is sine, the blue one is cosine. Notice that other than the fact that cosine starts at the point 0, 1 on the y, so the y-intercept of the cosine function is at 1, and the y-intercept of the sine function is at 0. Other than that, they are pretty much identical. If I add pi over 2 to my cosine function, actually I need an internal shift, right? So I need to subtract pi over 2 inside. And what just happened? My sine and my cosine lined up. So sine and cosine are just horizontal shifts of one another. They both have the same period. They both have the same range and domain. Cosine, however, because it is shifted, turns out to be an even function. Let's go back out to Desmos and remind ourselves what that means. So I want to just look at cosine. Take this off. So notice if I look at, for example, an angle of negative pi and pi, we get the same cosine. Pi over 2 and negative pi over 2. That angle there and the corresponding one right there, 0.77 and negative 0.77, both have a cosine of 0.718. Cosine is an even function. So the cosine of negative theta is equal to the cosine theta. These things down here at the bottom on both of these slides are called the negative angle identities, and you want to memorize these. Memorize this, okay? And memorize this. By now you will have completed your first exam, and you'll realize that you do need to memorize what I've asked you to memorize. Part of this class is internalizing this information, so no notes or reference cards on tests. We want you to remember and learn. Okay, so here's the comparison. The only thing I don't have on here is that sine is an odd function and cosine's an even function. I want to take a look at some transformations of sine and cosine. So let's start with sine. So I'll move that. So let's start centered at the origin. So I've got my circle here. It's centered at the origin. And if I take my radius back to 1, we get our usual, this happens to be sine function. I know this because it goes through 0, 0. And I'm only looking at a small portion of the sine function because I want us to focus on what's going on. Let me put on here. So I just threw on a standard sine function for comparison. All right. Now I want to change something. I'm going to make my circle bigger. What do you think is going to happen? Yeah, the maximum and the minimum are going to change, right? So if I make my radius be 3, what's that going to do? It's just a vertical stretch. What happens if I move my circle up off so it's not centered on the origin? Say I move it so that the center of the circle is 4 feet up. Well, now my height, my sine function, sine is related to the height of the circle of the point, right? Well, if we start here on the x-axis and start here on the horizontal and start moving around, we see we start at 4 and we alternate between 7 and 1. So the center line is shifted up by however far our center is elevated off of the origin. So what we're saying, what we're really looking at here are vertical stretches. We can also compress by making our radius smaller, yes? And vertical shifts. So vertical shifts and stretches. And those are pretty easy to understand in terms of the geometry of our unit circle. Now, pretty quick, we're going to move away from this, but I want you to understand the relationship at this point because it's handy for solving problems. we can look at this same thing for cosine, and we're going to see that cosine behaves pretty much the same way. So let me throw on a standard that is an unshifted cosine curve, or untransformed. So if I move my circle down, let's say I center my circle at -3, you can see that my cosine curve just moves down. And if I make my circle bigger, you can see that my cosine curve gets stretched vertically. So based on the minimums and the maximums, we can determine, this is called the amplitude. The amplitude is the height or the distance between the maximum value and the minimum value. But when we see a sinusoidal curve, we can always relate this back to a standard sine or cosine function. And the magic is we actually get to choose. So let's look at an example here. We've got a circle of radius 3 feet. It's mounted 4 feet off the ground. And the point closest to the ground is labeled P. We want to sketch a graph of the height above the ground of point P as the circle is rotated. So what we have is, and sorry, I don't have a fancy dancy schmancy drawer here, so you're going to have to put up with my bad art. Okay, that's really bad. Let me try that again. Whoops. All right, let's see what I can do. Nope, I can't draw a circle today. Pretend. Okay, so this thing is centered at the point 0, 4, right? We're talking about this point right here, this guy. That is at what? Well, radius is 3, so this will be at 0, 1, right? What we're talking about is as this guy goes around the circle, we want to sketch its height. So it starts at 1, right? So let's do this. Well, that's a bad origin or bad coordinate system. Let's use Desmos. Okay, new graph. So our circle. We know our circle is mounted 3 feet off the ground, so it's centered at the point 0, 4, right? That's its center. Let's put on our circle. We know that a circle, it's got radius 3, so that means 3 squared is equal to x minus 0 squared plus y minus 4 squared. Yes. So that's my circle of radius 3 centered at the point 0, 4. The point that we care about, this point P that we're interested in, starts at the bottom, so that's of my circle, 0, 1. Now what I'm trying to graph is the height of that circle as it moves around the, or this height of that point as it moves around the circle. So let's put on some helpful units and make this a little more visible. Okay, so on my time graph, we start at what? Well, when we start at the point 0, 1. What happens as that point moves to a quarter of the way around the circle? So at an angle of pi over 2. How high is it? That is right here on my circle, 0.34. So let me put that in. So the height of that guy above the y-axis is 4 units, yes? What is the angle? So what angle do I have going on here? If I think about moving from here to here, how far did I go? That's 90 degrees, or a quarter of the circle. The circle is all the way around, would be pi over 2, so that's going to be, or 2 pi. 2 pi divided by 4 is pi over 2. So on my sketch of the height, what that means is I've got pi over 2 is my x-axis, because I'm going in relation to the angle, and my height is 4. Okay? So my green points, I'm going to make all these points be green. My green points represent the height of the circle, or the height of the point as it moves around the circle. Okay? Let's move my point on up. Let's go to, sorry, the top of the circle, pi over 0, 7. At that point, my height is 7 units up, and I have traveled a total of pi radians, right? Okay. Let's keep going around. Let's move our point clear over to the other side. So I've moved to the back side of my circle. I've gone 3/4 of the way around. So I'm at 3 pi over 2, and my height is again 4. And then if I keep going on around, to 2 pi, I'm going to get back to where I started. So what we can see, and if I were to keep going around, the same thing would happen. So we can choose, we can say this is a periodic function, right? So do we want to, we can choose, do we want to use sine or cosine? Well, we can really pick. We don't know how to do horizontal shifts so good. We only know how to do vertical shifts. We also know how to do reflections. We can turn things upside down with a -1, right? Let's see. Let's start with let's try a sine function. Let's see what a sine function looks like. Well, let's try making some modifications. What's the first thing we know we're going to do? We know we're going to add 4, right? Because we need the center point to go through 4. I don't like that. I don't like that because this is at 0. I really want it to be at one end of the circle or the other. So let's switch it to a cosine. All right, that's better. Now I need to make my amplitude match the radius of my circle. So my circle has radius 3. So I get that by multiplying by 3. Oh, hey, I'm getting close. What do I need to do now? I just need to turn the thing upside down. How do I turn it upside down? I do a reflection, a vertical reflection. So I make my 3 be negative. So we can describe the height of a point that moves around any circle by, well, around this circle, by the function y equals negative 3 cosine x plus 4. I hope that thought process made sense. Work it through and make sure you can duplicate this. So let's play this game a little bit. What is the midline and amplitude of the function f of x equals 2 cosine x minus 3? You got two transformations up there. Which one's related to the midline? And which one's related to the amplitude? So I encourage you to pause the video here and write down what you think is the answer. And we will take a look. This is a cosine. And so I've got, this is y equals a cosine x plus k. So my multiplier is 2. So my amplitude is 4. We go from lowest to highest. And my subtractor is 3. So I've subtracted negative 3. So the solid red line represents y equals 2 cosine x minus 3. Let me get the right thing. X-axis. And what you see here is the midline is at negative 3. The amplitude is from highest to lowest, which is 4, because we go from 1 to 5, so that's 4. So the midline is negative 3, which is related to the external modification or the vertical shift. The amplitude is 4, which is 2 times whatever we're multiplying by. So the amplitude is 2 times my vertical stretch. So let's do this again. Sketch the graph of f of x equals negative 2 sine x plus 1. Start with your midline, your amplitude, and whether or not you've got a reflection. Go ahead and do that sketch. Pause the video when you're ready. Start the video back up, and we will take a look. Okay, so let's turn off my cosine and my sine and adjust everything back to starting value. Whoops, sorry, I meant turn off my cosine. All right, I want my a to be 1, my k to be 0. Let's turn on sines here. Okay. And what I have is negative 2 sine x plus 1. And I hope you got that you have a midline of 1 and an amplitude of 4. Not negative 4, but 4. Amplitudes are distances. Okay. Let's talk now about period. I already mentioned this. The period of the sine function is the distance between peaks or between valleys. So it's the distance between those 2 points or the distance between those 2 points. Really, it's the distance between repeated values, but we specify it to be the distance between peaks or the distance between valleys. So for an unstretched or an uncompressed sine and cosine function, the amplitude is 2 pi. If, however, we have an internal multiplier, that amplitude, or that period, the period is 2 pi. If we put a multiplication inside my parentheses, that is going to be a horizontal stretch or compression, and the period is going to change. And the period is going to change to 2 pi divided by that multiplier. So let's play with that. Let me put a multiplier on here. Let's say I multiply by 2. What's going to happen is my period going to get bigger or smaller? Are my waves going to get closer together or farther apart? Let's see. They get closer together. And my period now is 2 pi divided by 2, which is pi. And you see that because you may think, well, wait a minute, those 2 points are still 2 pi apart. They are. But look at that, there's another peak in the middle. So if we look at the distance between peaks, it is reduced to pi. In other words, the number of waves that I get in the same distance has doubled. Okay? My amplitude, the height of my waves is unchanged, but the number of them doubles. Or if this were, say, 1/2, it takes twice as long to make a full wave. If this is, say, 4, then the number quadruples, right? So my period will be 2 pi divided by my internal multiplier. We can think of the period, if we think of the sine and cosine as graphs of how fast, graphs of the position of a point going around a circle in relation to time, then we can relate the period to how fast the point goes around the circle. Okay, so what is the period of this first function? F of t equals 3 sine 2t plus 1. All we care about is the period. The period comes from the internal multiplier, and the period is 2 pi over 2, or just pi. What about this one? The period is 2 pi divided by pi over 4, or 8. Okay? So let's put it all together. Let's write an equation for a sine graph for the sine function that has an amplitude of 3, a period of 2, and midline at 1. Well, we know we're going to have y equals something times the sine of something times x plus something. This one's easiest. This last one gives us the midline, so there's a 1. The amplitude is 2 times whatever we multiply out here, so this will be 3/2. And my period, I want a period of 2. And remember that my period is equal to 2 pi divided by this b. I want my period to be 2. So b is going to be 2 pi over 2, or pi. Okay? All right. Should we check me? I'm kind of nervous. Let's see. Let's see if I did that right. I need to add in another slider. Okay, so what did I say? I said, well, the first thing I want is I want sines, not cosines. I said that my external adder was going to be 1. I was going to multiply by 3/2. And I was going to multiply inside by pi. Now, okay, let's see if I got that right. I wanted an amplitude of 3. My function goes from sorry. My function goes from 2.5 to -1/2. So yes, that's 3. And I wanted a center line at 2, or center line at 1. And yes, I've got a center line at 1. And I wanted a period of 2. So that means that this point and this point should be 2 units away, and they are. So, all right, that wasn't so bad. We just need to understand how our transformations work. Okay, I'm going to leave this one to you because we've pretty much already done this. This same example is worked out in your textbook. I'm going to let you work on this. If you have any questions, let me know. What I want to do is talk about this one. Can we write the equation for this graph? Let's work it through together. And let's think about that. First question, is this a sine or a cosine? And how am I going to know? Here's what I do. I look at where we cross the x-axis. In the simplest case, this will either be a peak or a valley. If it is, or it will be a midline. Okay? We're not crossing the x-axis at a midline. We're crossing the x-axis at a valley. So this is going to be a negative cosine. Okay? Now, what negative cosine is it going to be? Well, I've got an amplitude of 6. I go from -1 to 5, so it's going to be a -3 cosine. Something times x plus something else. Where is my midline? Well, my midline is 1, 2. My midline's at y equals 2. Because my peaks are 3 units above that and 3 units below that, so that means I add 2. And what goes in here? Well, what goes in here comes from my period. Now I don't have, yes I do, I've got a trough and a trough. This tells me that my period is 6. Remember that my period is always equal to 2 pi divided by that b. That is my internal multiplier. It's going to go right there. So 6 equals 2 pi over b. So b equals 2 pi over 6 or pi over 3. And I'll leave that to you to check on Desmos. Make sure you can do this sort of exercise. And I believe that is, yeah, we just have some more of these. I'm going to leave these for you to work out. These should be in the text. If you cannot, and you can use Desmos to check your work. So go ahead and figure out the equation of this graph. And pause the video while you do it. And use Desmos to check your work. And this one. And we're going to talk for a minute about horizontal shifts. And I know this video is getting long. We are almost done. So I need to adjust my formula here. Thought I had one of these. Hold on. Yes. No. All right, we'll go back here. So I want to talk about horizontal shifts. And the way we talk about horizontal shifts is we put those inside the parentheses, and we put it in the same order that we would do the order of operations. So we were going to talk about horizontal shifts before multiplying. So this first function I'm asking you to look at, y, f of x equals 2 sine of 2 times x minus 3. So 2 times the sine of 2, all of this is not new. What's going to be new now is this. How many units are we going to shift when I put in minus 3? I shifted what? Let's look at my 0, 0. I know that on sine, I should cross the center line. Sorry. Right here, yes? This point, 0, 0. When I subtract 3, where does that point go? Oh, isn't that handy? It moved 3 units. So this is the one that moved, okay? This guy right here. That's why we put our shift inside the parentheses. So whatever we have added to my x results in a horizontal shift of that many units. It looks weird because it's backwards, as horizontal shifts always are. But we just, so for this first one, we shifted 3 units. Now this gets a little tricky when we talk about something like this. How many units is this going to shift? It's only going to shift 2, because we need to remember that our basic form, if I put this in basic form, it would be 3 times the cosine of, factor out a 4 here, x plus 2, and we'll see that we have a horizontal shift of 2 units. So this one's got a horizontal shift of 3 units. This one, factor out the common denominator here, and the common denominator is going to be, actually factor out what we multiply the t by. So pi over 6, t minus, and now pi over 2 divided by pi over 6 is going to be 3. So this guy's going to have a horizontal shift of 3 units. And this one has a, so put it in standard form, which means factor out whatever is multiplying by your variable inside your parentheses. And we have a shift of pi over 8 units. Play around with Desmos and graph these for yourself. And I'm going to leave you with one last exercise. Let's talk about how we would, actually we're going to do, yeah, we're almost done. This is getting too long. So what have I got going on here? Let's talk about this graph. Where is it centered? The center is at the x-axis, so y equals 0. What's its amplitude? Amplitude is 2 times this, so that's 6. What's the period? The period is 2 pi divided by whatever is multiplied by my variable. So the period is 4. And what's the horizontal shift? Horizontal shift is 1. Okay? All right. Let's try doing this in reverse. Let's write the function of this graph, and then we'll be done for today. Be sure you know how to do all this stuff. Okay. Now that we have all of our shifts, we can actually choose. You want sine or cosine? It doesn't really matter. We can choose either one. So there's going to be more than one right answer to some of these. So like this one, let's look at this point here. Let's say that this is a sine. Let's say that this is going to be y equals something times the sine of something times x plus something. Whoops, I need more space in there, don't I? Because I'm going to have that, right? So if this were a standard sine curve, this point would be my midline point, and it would be down here. So right away, I know I've got a +1. And I know I've been shifted to the left 1 unit, so this is also going to be a +1. Now you could also say we were shifted okay. This is also going to be an upside down. But you could say that you were shifted to the right 5 units too, and then you put in a -5. And then you'd have a slightly different answer, but it would be just as valid. So let's work this one through first. Now, what goes in here? This is my period. So how many units is it from one peak to the next? 12, right? So my period equals 12, but I also know that my period is 2 pi divided by that internal multiplier b. So 12 is 2 pi over b. So that means b equals pi over 6. Yes? Now, amplitude. Amplitude is related to the distance from the trough to the peak, which is 1, 2, 3, 4. So amplitude is 2. And because I chose a shift to the left, and because I know the sine looks like this, I need to turn this guy upside down. Now, I also said that you could choose to shift this the other direction. So let's just take a look at that real quick. So I chose that point just to the left of the origin as my midline point. Let's see if I choose this one. Okay? If I choose that, then I'm going to have y equals, my amplitude is unchanged. The only thing that's going to change is what goes inside, because now I'm looking at this as a rightward shift of 5 units as opposed to a leftward shift of 1 unit. Everything else is the same. There is a relationship here. We'll talk about this later. Be sure and check me. Plug these into Desmos. Make sure you can do this for yourself. There are plenty of exercises to practice on in the textbook if you want more practice. And message me with questions. I will talk to you all again soon. Have a great day.